we are going to briefly discuss some of the applications of carbon fibers. So now we already know how do we fabricate carbon fibers. We either perform melt extrusion or we perform electrospinning, and then we heat treat these polymer or pitch fibers to get carbon fibers. Okay, now after that we will also perform certain characterization tests. We will also learn about the mechanical characterization of carbon fibers. But let's briefly first talk about some modifications that you can do during the electrospinning or melt spinning process. And then why do people do these modifications? Because there are certain applications associated with them, or there are certain applications which require a certain type of fiber, not just a simple carbon fiber. Okay, so I will talk about some of the applications. I cannot cover all the details because there are actually many carbon fiber applications in both manufacturing industry as well as device fabrication, micro nano device fabrication. You can also make membranes and filtration columns also with carbon fibers. So there are so many applications. You can easily do an internet search and look for a variety of applications. In fact, every day something new is coming up. But what we are going to do here is we will talk about like the fields where we have these applications. So what are the possibilities with carbon fibers, let's say. Okay, so the next lecture is going to be about carbon fiber based composites. A lot of manufacturing related applications are actually they do not utilize carbon fibers directly, but in the form of a composite material. Composite is when you have another material mixed into it, a binder or a matrix phase. We are going to talk about all of that. So manufacturing applications for now in this lecture we are not discussing. Okay, first of all, as I told you, there are certain properties of carbon fibers. That is what these are the properties that make them so interesting for us. So I told you that these are lightweight and strong materials, and they are electrically conductive, and they have also similar electrochemical properties like our other advanced or graphitic carbon materials. So these are some of the properties that we are going to utilize. Now, once we fabricate our carbon fibers, how do we, what tests do we need to do? What are the properties that we need to immediately see? Okay, why, what are the applications of this particular type of carbon fiber? Because each carbon fiber can also be different depending upon the crystallinity, the heat treatment conditions, the nature of precursor, and so on. And also the diameters, of course. So first of all, we test the mechanical strength of our carbon fibers. So mechanical strength, you will not, for manufacturing applications, you will typically not test the mechanical strength of individual fibers because you're almost always using them as bundles or ropes. So these threads or ropes or bundles, whatever you call them, what we do is whatever is the required diameter of our bundle, then we take that bundle and then test its tensile strength. Compressive strength also becomes important, but primarily tensile strength. Okay, then we also want to understand the electrical properties of these fibers. Electrical measurements can be done when again you take the fiber and pass current through it. There are many devices where you can do this also for individual fibers, or you can do it for the bundle of fibers depending upon your requirement. What is also very important, and for a lot of applications, what we use in the case of carbon fibers is their surface area. So you know that for different applications, for example, electrochemical applications, surface area becomes very important also for sensing applications. This was something we also learned in our porous carbon lectures. In fact, we induce porosity, we increase the surface area because that also increases the absorbance of these kind of carbons. Now, if you already have fibers already exhibit a very high surface to volume ratio. If you further induce porosity, then you can have a very high surface to volume ratio, and this is also one property that can be used when it comes to carbon fibers. And of course, something very much related to this is the addition of surface functional groups. So if you want to use these carbon fibers as adsorbents, then what you can do is you can also chemically induce certain functionalities on their surface. So they become, for example, more hydrophilic, which is important also for electrochemical applications. So your entire electrode gets wetted properly. So these are some of the properties of carbon fibers that you can play with if you want to use them, especially for device applications. As I said, that the large scale manufacturing applications we'll talk when we talk about the composite materials. Okay. Now, if we think about the mechanical strength of the fibers, what do you think limits the mechanical strength? Why don't we have all carbon fibers which have the same exact same strength? That will, similar to all carbon materials, even in the case of carbon fibers, one thing that determines the mechanical properties, also electrical properties, but mechanical, is the crystallinity. So heat treatment temperature increases, then the graphitic content increases, then the stiffness of the material increases, then you have higher modulus materials, carbon materials. So that is something which is also valid in the case of carbon fibers. So as you increase the crystallinity, you get higher stiffness. But also there will be some other things, and that will be sort of important. You will have a critical diameter of your fibers, because fibers bigger than that may be able to, or thicker than that, may contain more what is known as defects. Now, what is defects? What is the microstructure of carbon fibers? Carbon fibers, as I had shown in one of the previous slides, I think when we were talking about melt extrusion, that you have different possibilities depending upon your fabrication parameters. You have different possibilities of arrangement of crystallites in the case of carbon fibers. So it is different slightly from the bulk carbon materials. Also, the defect annealing patterns are different compared to the other bulk, graphite or glass-like carbon, or active, char-like carbons for that matter. Okay, so what happens is this defect, these defects or voids, we also call them flaws, because defect is something which is, we are typically talking about atomic level, but here we are talking about bigger, larger voids or regions of non-crystalline material. So these kind of materials can actually limit the properties of your mechanical strength of your carbon fibers, because this is where you have a slippage. This is where you can actually break the fiber when there is strength. So whenever you have these kind of sort of voids or flaws, when you pull the fibers, this is where the fracture takes place. Okay, so for example, when you fabricate polyacrylonitrile carbon fibers, then sometimes you will have these lumps of polymer. So you have, at the end of the day, you have chains in the polymer. You have chains of polyacrylonitrile. And then you are preparing a solution in DMF. You may not have the perfectly uniform solution. And you may end up having here and there certain lumps or non-uniformities in the solution, and that is why you may end up getting these kind of bulges in your carbon fiber. So now I have circled this region. You can see that this is where the necking takes place. So this is your weaker region. When you pull the fibers, there is a higher probability that it will break from there. And also these bulges will not, they may contain some of these flaws or defects, large scale defects, because they do not have the same surface area as the rest of your fiber, and that is why also the defect annealing pattern, the byproduct annealing pattern, everything is different in that bulge. You may actually have some even the purity of that bulge, if you just compare it with the thinner region of the fiber, same fiber, you may even have different purity, because now the byproduct annealing patterns are also different in that bulge. So these kind of bulges, which you will see very often, especially if you have certain humidity in the chamber, or you are not, or your solution is not uniform, especially when you have more viscous solutions, you are going to higher concentrations of pan. In that case, you will see these kind of bulges a lot, and these are macro defects. You can actually see them. In fact, that is the reason people often use this horizontal electrospinning setup, because these are then heavier fibers, which at least most of them will fall before reaching the collector electrode. Okay, you can also have, if you look at inside a transmission electron microscope, you look at the microstructure of your fibers. In that case, you can also have, like I have shown again with a circle, you can have these kind of regions where you do not have any graphitic planes. You can call it an amorphous region. You can call it a region with randomly oriented, random bond lengths of the atom, but you do not have sp2 type hybridization, or you also do not have any graphite crystalline. Now, overall, when you look at a fiber like this, so this is a very small region. You will, altogether the fiber will look uniform, and you will also even call it graphitic carbon fiber if you're able to observe the peak for graphite in your XRD. So you will be able to still call it a good fiber, and this is graphitic fiber and everything. But when there is any tension after or fatigue or any kind of mechanical, whenever the deformation takes place, this is going to be, these cracks or these voids are going to be this is where you're going to have your cracks and breakage. So these are the possible defects in the case of carbon fibers. Some of them we can avoid and some of them we can actually not avoid. But that is also the reason we are not using single fibers and we are rather using bundles of fibers. So if one of your fibers breaks, you still have others. And in a rope, if one fiber breaks, others can still hold the structure. So, however, this is where you have the problems with the mechanical properties. Okay. Now, as I mentioned already, crystallinity can be controlled. Number one, by heat treatment temperature, and number two, also by choosing the right precursor. In the case of fibers, we are relatively limited because we also need to see the spinnability and manufacturability of the fiber of the polymer, but we can choose at least the right concentration. We can choose our precursor in such a way that we get that we get good fibers out of it. So that is these are crystallinity we know how to control. Now, flaws is something that is not easy to control. However, as the diameter of the fibers gets smaller, then there is a lower probability of getting the flaws, because these flaws are often, they are larger, like they are 50 nanometer, for example, in size, 50 to 70 nanometer. In that case, if your fiber itself is, the diameter of your fiber itself is 100 nanometer, then there is a very, very small probability that you will have a defect that is 50 or 70 nanometer. So what you can do is, one thing is that you can reduce the diameter of these fibers. Now, how do we calculate the approximate size of these flaws? There is a method proposed by Reynolds and Sharp, which we will briefly discuss.
So when we talk about the mechanical properties of carbon fibers, especially pan-derived carbon fibers, it's interesting that they do not necessarily show an increase in their overall value when we increase the carbonization temperature. Okay, why? Okay, now you should understand there are two important parameters. Number one is your Young's modulus. Now, Young's modulus, what is it? You have, this is the slope of the stress strain curve. Okay, so that is your Young's modulus, which keeps on increasing as you increase the carbonization temperature. So here in this curve, you will see that you have this profile. So basically, this is your carbonization temperature. So above 1500, you do have increase in the Young's modulus. However, it is not very sharp increase. The curve almost flattens, but there is a certain increase. There is another property which is known as the tensile strength. What is tensile strength? That is basically, whenever you're thinking in terms of a wire or fiber-like structure, maximum stress that your wire can handle, that your fiber can handle. Above that, it will break. So that is your tensile strength. Now, if you see this curve, then the tensile strength of your pan-derived carbon fibers, it increases up to, let's say, 1500. But after that, it indeed declines. It decreases. So in many applications, what is more important is the tensile strength rather than the Young's modulus. So depending upon the application, you need to select your fabrication parameters, your heat treatment parameters, because it's not necessary that just increasing the modulus is important for your fiber. Okay. Now coming to this flaw size that we were talking about, this is the Reynolds and Sharp method, or the formula that is given by them. What is the flaw size again? This is the size of your trapped defect in a carbon fiber that would limit its mechanical properties, and this here is the relationship. This is Young's modulus. Gamma G here is the surface energy of graphite, which is approximately 4.2 joule per meter square. And the sigma F is the tensile strength of an individual fiber. Okay, there have been certain modifications to this relationship, and people have, instead of considering the surface energy for graphite, people have also considered the surface energy that is experimentally calculated for a set of carbon fibers or a type of carbon fiber, or the ratio of surface energy of carbon fiber to that of graphite. However, one thing that is clear from this relationship: your flaw size is indeed directly proportional to the Young's modulus. What does that mean? That means that if you increase your pyrolysis temperature and you get the Young's modulus that is very high, you may actually also get larger voids in it. This, however, this relationship may not be valid for ultra thin fibers, because there you have defects annealing out very easily. However, if you have 1 micrometer to 5 micrometer diameter fibers, which is often the case with industrial carbon fibers, indeed you may get some defects when you increase the carbonization temperature. Why does that happen? What happens is, in the beginning, when you have when you've heated your carbon polymer fibers to about 1000 degrees, at that time what you have is these turbostratic carbon sheets. What are turbostratic carbon sheets again? These sheets are also graphene-like, but they contain several defects, and therefore they are not organized in an A fashion, as in the case of graphite. You rather have them, the spacing between these lines is slightly higher than what you would get for graphite structures. Okay, these type of carbon materials, this type of carbon structures, the arrangement is known as turbostratic arrangement, and the carbons that have that kind of arrangement are also sometimes called turbostratic carbons. Okay, so you have turbostratic structures. Now you increase the temperature. What will happen? Some of them may actually align and form graphite crystallite. However, now when this space decreases, the overall structure, because the spacing between the sheets is now decreasing, what happens is there may be some voids created because we are not supplying any material from outside while our structure is shrinking, and it is shrinking in random ways. It's not necessarily one big graphite crystal that is forming. So you may end up getting certain voids or certain flaws. Again, if the fiber is very thin, there is a high probability that some of these flaws will anneal out. Also, in the case of thicker fibers, some of them will anneal out, but not all of them. Some may remain trapped, and these are then your weak points in your fiber. That's where your fiber will break. Okay, so this is just to tell you that just increasing the carbonization temperature is not enough. By the way, one more thing, this relationship is not necessarily valid for fibers that are prepared below 900 degrees. In fact, anything that is prepared below 900, we may not even call it carbon fiber. We just call them, they have a lot of impurities. Okay, so they are like intermediate materials that we had discussed earlier. But these are only valid for type 1, type 2. By the way, I don't think I have told you what are type 1 and 2 and 3 fibers. So type 1 carbon fibers, so these are the industrial names, are prepared at approximately 1000 degrees centigrade. Whatever is prepared at, let's say, 1500, that is known as type 2 fibers, and type 3 fibers are those prepared above 2000 degree centigrade. So you can decide which type of fiber and what are the conditions that you require for a certain application.
Okay, so now you already know that if the diameters are smaller, then there is a lower probability of getting the flaws. Okay, now let's talk a little bit about what we can do to our electrospun fibers, what modifications we can make in the polymer precursor, and that's how we can get more what you can call advanced carbon fibers. So basically they are somehow better or different or more improved compared to our standard regular carbon fibers. Okay, so what are the things? I mean, you can already imagine what are the things you can do. Okay, because we have this flexibility of carbonizing. So carbonization process, heat treatment process always gives you, you can tune a lot of properties. That is one of the most important things about carbon materials in general, that you can tune their properties by playing with the parameters of the heat treatment process. So one thing here you can do when it comes to carbon fibers, you can, for example, make a fiber which has a core shell-like structure. What do I mean by core shell? You have two different polymers. So there is one polymer which makes the core and the other one makes the shell. Okay, how can you do that? Actually, it's not that difficult. Electrospinning setups, even they come with these what is known as coaxial spinning, which means you have two concentric cylinders or your needles. So when you have a spinneret, you can have two different polymer jets going out at the same time. So in that case, what you can do is you can choose your core in such a way that it does not carbonize very well. So it is a low carbon containing polymer. At the same time, you can choose your shell as a high carbon containing polymer such as PAN. What will happen once you carbonize these structures? During the heat treatment, your material, the core material, will sort of, because it does not give good carbon anyway, it will disappear to a great extent, if not completely. And then your shell will remain there as a carbon fiber. And in fact, these kind of experiments have been done. This is a very, very beautiful picture you see. You have a hollow carbon fiber now. Hollow carbon fibers will offer a lot of interesting properties. For example, first of all, their overall density is so much lower. We always want to have high mechanical strength but low weight of our carbon fibers. So if you have hollow fibers, you can imagine the weight goes down so much. Your density of the overall, bulk carbon fibers is so much lower. You can also you can use these for a lot of biomedical applications, drug delivery applications. Basically, you can trap a lot of things inside these hollow cylindrical structures or hollow fibers. You can also use these structures for supercapacitor electrodes, for battery electrodes, for any application where you require a high surface area. Now you open up so much more surface area in the case of these kind of fibers. So this is one thing that you can do with your with the carbon fibers. What you can also do is you can mix a lot of additives. So any nanoparticles or even other carbon structures. I showed you in the previous slide that you can add carbon nanotubes. You can even add graphene flakes. You can add various nanostructures into your polymer solution. So when you're making your PAN solution, you can already mix these things inside your PAN solution and then spin fibers out of it. Of course, you will have to optimize. The most important thing is to optimize the concentration of your additive, because if it is too much, then the polymer will lose its spinability. But once you optimize this concentration, now you get fibers like what you see in this image, that you have a lot of these kind of fibers are known as decorated fibers. You will hear this word in the literature, that you have carbon fibers decorated with certain nanoparticles, or glass-like carbon electrodes decorated with certain nanoparticles, or many other structures, whether they're large scale or small scale, they can be decorated with nanoparticles. So this is also another thing you can do. Why would you do that? Because now your carbon fibers basically serve as the sort of a substrate for these nanoparticles. Maybe there is a certain nanoparticle, you want to utilize the property of the nanoparticle and not that of the carbon fiber, or you want to utilize the property of both. So carbon fibers are conductive. If you have high heat treatment temperature, then you can have conductive carbon fibers. Now you can pass current through these fibers, and let's say whenever you have, or you can even perform Joule heating, because if you can pass current through certain fiber, then you can heat it also by Joule heating. So in that case, maybe at a certain temperature, your nanoparticles become activated. Those nanoparticles can then perform sensing of different types. You can, for a number of biological applications. So biosensors is a class of devices where you are somehow sensing a biological entity. That biological entity can be a virus, can be a bacteria, or can be a lot of things. Also, you can sense certain types of drugs, the concentration of these drugs, and so on. So for a number of these applications, biomedical applications, you will utilize these kind of decorated nanoparticles. This is also one possibility that we have. Okay, we can perform surface activation. So you know that we do physical surface activation using steam and carbon dioxide. You can do that also for the carbon fibers. And you can also use certain chemical methods. You know that when you do chemical activation, then you, during the, when you're preparing the fibers in the polymer itself, you'll add certain chemicals and then carbonize them. So both, whatever you do for porous activated carbons, which we learned in some of our previous lectures, whatever you do for activated carbon, porous carbons, the same thing you can do for making activated carbon fibers. By the way, also polyacrylonitrile derived fibers can be activated. So it is not necessary that they have to be derived from cellulose or rayon. Different types of carbon fibers can be activated. So these are some more possibilities that you have. Of course, you can make different types of mixtures of carbonizing, non-carbonizing polymers, like I showed in the hollow cylinder there. These hollow fibers had the core shell-like geometry, but if you just make a mixture and then perform the electrospinning, then carbonize it, what you will get is highly porous carbons. Then you go on activating these porous carbons further, then you can imagine how much surface area is available for your application. So let's now talk about the applications. As I mentioned, we will not talk about the composite applications for now in this lecture. Carbon fibers can be directly used for a lot of applications. Why do we, in the manufacturing applications, the fibers are used with certain resin because you need some lubricant for braiding them, for making the fabric out of them. Otherwise, you may end up damaging your fiber, mechanically damaging your fibers. Also, they are rough, they are hard and brittle. It's not that easy to process them without a resin. That is a different thing. But of course, when you use the resin, you will lose some, some of the surface properties of your carbon fibers, for example. Even mechanical strength, overall mechanical strength will be reduced because now you also have some polymer mixed into it. So you don't have 100% carbon fiber mass. So there will be some loss of property. But in the case of micro nano device applications, we in most cases directly use the carbon fibers. We don't use them with the resin. And if we, for example, making a biosensor, I will come to it, you can use the fiber with a little bit of polymer or resin in it, but in that case, that polymer must be biocompatible. Okay, so we will see some examples here. One example is, so I have not given any specific example, but there are publications that you can search for. You have these ultra thin carbon fiber mats that can be used as cell culture substrate. So in case you don't know, cell culture basically means you're artificially growing cells of different types, cells and tissues. So you're doing it outside of the body, which is known as the in vitro studies of all kinds. And what you do is you're trying to grow the cells. And why do you do that? To see the effect of certain drug, for example. Before we start testing in animals and humans, we often test it on the cell lines or these cultured cells. Cell culture can also be performed in a liquid because we also need to provide some food to the cells, right? And this food may contain glucose, this food may contain certain antibiotics, and also whatever is required for the cells. Okay, so this is what is known as cell culture medium. Also nutrients, a lot of things are mixed into the cell culture media. Now you can also, so cells will float in that medium and they will culture directly. However, in the actual biological environment, cells are not really floating. In our body, they have a solid support. And to mimic these biological conditions, we sometimes use what is known as cell culture substrates or scaffolds. So substrate, you will say, when they are 2D, and scaffolds are also basically substrate, but 3D substrates. So for making these cell culture substrates as well as scaffolds, sometimes the carbon fiber mats are directly utilized. Now here the property of carbon, that it is inert, becomes very important because cells will typically not like anything that can react with them. Then they will they can have certain chemicals that come out of these substrate materials. Then they do not like it. But in the case of carbon, it is so inert that cells, it does not bother the cells. So it functions as a very good cell culture substrate. So there are various examples where carbon fiber mats are used as substrates. Okay, now again, biocompatibility also can make it useful for biosensing applications. So for biosensing also, biosensor in itself there are many things about biosensor. There are many types of biosensors. Some of them utilize the electrochemical properties of the substrate material. Some of them may not have actual substrate or even any cells or any biological moiety, for example enzymes attached onto them, but they may just use some kind of nanoparticles which are sensitive to certain biological entity. So those are also biosensors. That there is a variety of biosensors, enzymatic, electrochemical being the most important ones. For biosensing applications also, you can directly use carbon fibers. Now you may use the mat, the carbon fiber mat, the fabric-like structure, or you can also use here the tips of your carbon fibers. Why would you use the tips? Because there now, then you can actually use these nanoscale tips. Let's say your fibers are nanoscale. Then you really are able to sense even very small concentration. You can sense the individual biological entity that you're planning to sense. So what you do is you take a fiber bundle and then you put it inside a glass capillary. In this case, occasionally people will also mix a little bit of resin again because you want to put it inside the glass capillary. It's like when you put a thread inside a needle, that kind of thing. So you try to make the thread a little bit harder so that it can go easily. So here in this case, some resin may be used. Of course, it has to be biocompatible. Okay. And now you can also fabricate a number of different micro scale devices. So micro devices, again, you can have electronic devices, you can have sensor devices, you can have various different types of devices. It's not like micro device is one thing. Here, I'm just trying to show that how you can use carbon fibers for these devices. Of course, one option is that you can use the entire fiber mat and then you can use them. So there are a lot of examples where these mats have been used as electrodes for supercapacitors and batteries. That is example one. And then also what you can do is you can utilize single fibers as well. Where here in this image you can see that this is a combination of photolithography and electrospinning. So the electrode pads, you see there are two lines and then there is a suspended fiber on top of them. So the fiber was prepared by electrospinning, while these electrodes, they were patterned using photolithography. So now you already know about photolithography. You have certain phenol formaldehyde resins that can be converted into carbon. If you also have a fiber suspended on top of them, then this entire assembly can be converted into carbon. So now you have the entire carbon structure, and now you can perform your sensing using that individual fiber. You can even perform Joule heating on top of that fiber, and you can use it as a CVD substrate, for example. So there are multiple applications where you can combine other microfabrication techniques with electrospinning. You can also take the electrospun cloth-like fiber, or woven or non-woven, and then you can perform etching of that fiber and then do the micro patterning, and then you can make these ultra flexible devices which can be used for sensing purposes. So this is an example where we used it for neural sensing purposes, but there are many other devices that are possible using micro patterning of carbon fiber mats or carbon fabric. Okay. You can also have some biomedical implants which are mainly again fabricated using the composite materials, because they are load bearing and they also need to stay inside your body. The problem with carbon fibers is that they do not degrade. So if you make a ligament implant, for example, ligament or tissues can grow nicely on top of it. So it provides like a template and the tissue can grow nicely on it. But the problem is that now afterwards you will have to surgically remove it because it will not degrade and excrete out of your body. So you have to surgically remove these carbon implants. So here the inertness and stability of carbon is also a little bit of a problem. But ligament implants nonetheless are fabricated using carbon fibers. Again, some resin may be used in that case, and you will typically use a woven carbon fiber mat and not the as spun fiber mat. Okay, other devices are membranes and filtration devices, and again you can activate the carbon fibers. That increases the adsorbance and porosity, microporosity. So altogether you can use it for a number of applications. Electrodes I have already mentioned. So these are some of the applications of carbon fibers. In the next lecture we are going to learn about carbon fiber composites.